actually, I can just present and we can use the
Oh,
video.
it's much better because the video was,
Yeah.
the sound was very low. So if you
Okay, yeah, I
can,
think the video should start back up, so I
but
can
I
share.
cannot introduce you, Kate, because
Oh,
you didn't
okay.
send me. So you introduce yourself. You don't,
Oh,
if you
yes,
don't mind.
sure. Sounds good. Thank you.
Okay. Sorry for
Yes.
that.
Oh, no worries. Thank you. Howdy, I'm Professor Kate Davis at Texas A&M. Let's see, so I joined A&M in 2017. Before that, I worked for Power World Corporation for like about 9 years, and I'll be presenting our paper on behalf of our team here. So most of the work done on this paper was done by Arnav, who was working on his master's thesis. He actually graduated and is now working for Apple. So yeah, he was good. Okay. So today I'll just go over briefly what is presented in our paper, and please feel free to take a look at our paper for more details, and please feel free to contact us with any questions. That even if you have them after this session, feel free to email us. So the main focus of our work in our paper is on detecting false data injection attacks, and actually the earlier paper that was presented by Theodorus I thought was really great and interesting presentation. I was actually just messaging all my students like, oh, you guys should read this paper. So I think that really motivated it well. So basically false data injection attacks, the idea is to alter the measurements in such a way that the state estimator thinks that the power system is at one state when it's really at another state. And so one way you can think about this is a false data injection attack. A really stealthy, unobservable false data injection attack is finding another feasible power flow solution and sort of like tricking the state estimator to converge on that solution instead of the true state of the system. And there are lots of different ways of making false data injection attacks. And the focus of this paper is actually on their detection. And so what we want to do in detecting false data injection attacks is we want to take advantage of the fact that we as the defenders or as like the operators know how the system should respond to perturbations. And so when its measurements don't respond in the way that we expect, then that could indicate that there's an attack on the measurements. And so essentially what we need to do in detecting false data injection attacks is take advantage of the fact that the data is changing over time. So we want to use the value of data over time to detect attacks rather than looking at snapshots. So you can kind of generally think about this approach as like a probing or perturbation-based approach. So we want to take advantage of perturbations in the system and basically notice when the system doesn't respond in a way that's consistent with how these perturbations should look. And so that's kind of like the intuition behind the detectors presented in this paper. And in particular in this work, in this paper, we're looking at deep learning based detection of these attacks. That's sort of the intuition, is to take advantage of the ongoing perturbations and use deep learning to our advantage to detect these. And so there's a lot of work in the area of false data injection attacks, both in the attacks themselves and in the detection. And some of the previous methods include like classification methods, and there's forecasting methods that use linear models. And then there's also has been some unsupervised anomaly detection. And what we really want to do in this paper, in this work, our focus is that we want to be able to avoid this problem of needing labeled training data for supervised models. And so what we're after is an unsupervised approach. So in real power systems, not going to be feasible probably to create labeled training data which capture all possible attack combinations. And so we want to use unsupervised methods because they don't need labeled training data. And so in this method, the idea is the following. So the defense mechanism that we propose and we explore in detail in this paper is to use autoencoder based neural networks to basically do this sort of intuitive concept of probing the system that I talked about, but use sort of like the power of neural networks to do it. So the idea is that we have this input X, which are the measurements, and those get compressed to this hidden state, and then they get decompressed again. So there's an encoder and then there's a decoder. And basically the idea of this mechanism, which is called an autoencoder, is to get the same thing on the output as you get on the input. And so so basically it filters out noise. And so the model minimizes the reconstruction error. That's the difference between the input and the output of the model. And so basically, if we apply this type of detector on data where there's a false data injection attack, then it should be like very, very clear in the reconstruction error that there was an attack, because the autoencoder should just be getting back basically the good data. And so by looking at the reconstruction error on the autoencoder, you can find where the bad data is. And so that's sort of the idea, is to explore using this autoencoder with neural networks for false data injection attack detection. And in the paper, we present in particular 3 different ways of doing this with different encoders and decoders. And so the first method is an ANN autoencoder that uses fully connected layers. And this method is really considering the spatial aspects only. And then we also use an RNN-based autoencoder that considers spatial and temporal aspects. So this has LSTM layers. And the thing that's in common about all of these autoencoders is that you're basically taking the input and compressing it to this hidden state and then decompressing it. And then in this process, the false data injection attacks would become detected. And then the third defense mechanism that's proposed is what we call the A3D. So it's attention-based autoencoder. So it's sort of like building on the first 2 methods, where it's considering spatial and temporal, where there's special weightings that are learned that take advantage of the fact that in power systems, the future state is going to be somehow dependent on the past state. And so the attention mechanism allows us to learn what those weights are and should do a better job with detection. So there's sort of like two parts, I guess, in identifying false data injection attacks. So the first part is detection. So we want to detect that there's an attack. And the second part is location or localization, which is we want to figure out where in the system the attack is. And this paper looks at both aspects of this problem using these autoencoders. And so in locating false data injection attacks, and this goes back to the understanding about how they're constructed and how power systems work. Basically, if you have devices that are connected to other devices or connected to other buses, then this reconstruction error would show up on the nearby devices. And so it makes sense to group the devices together and look at the detection on those groups rather than just on all the devices. And so this figure here is showing, like, if we want to localize I, like bus I, what does that mean? It means the devices at bus I and the devices on the branches, and then bus J would be the devices on that bus and devices on the branches. And so basically it matters how the devices are connected and doing the localization. So in the experiment, So in the paper, there are experiments done on a 14 bus case with measurements across its 39 devices. And let's see, so it's attacked with the least effort random attacks. And the attack devices are 4, 8, 12, 16, and 20. And then there's also some attacks introduced with an unknown or random number of devices compromised. And then in the evaluation of the results, what this paper was doing is wanting to have a high recall. So what this means is that the evaluation metric was tuned so that we don't want to miss any attacks, basically. So we'd rather have false positives than miss an attack that's actually there. And we also use something called F1 score, which is a harmonic mean of the precision and the recall. So yeah, so basically the goal in this case was not to miss any. So that's how the algorithms were tuned. And so this is a look at the detection results. So for detection, we compared the 3 autoencoders and then these other methods, and we can see that the autoencoders do a really good job of detecting the attack as we would expect. So that's good. And then we looked at localization, which is kind of interesting. So for localization, what you see, which is actually what you would expect to see, is that when you do this like decompression from the hidden state back to this like full state space, what happens is the reconstruction error gets spread out to the neighboring devices or the neighboring buses. So if you just try to use this approach to do localization per device, it can be, basically it'll look positive at all of the devices around where the actual attack devices are. And so you can do a little bit better than that for localization if you cluster the devices by bus. So so the figure 2 at the bottom shows like the detection results using the localization at the bus level. And so here again, like you will see a positive at the bus where the attack is, but also at the neighboring buses, which is interesting and also makes sense if you think about how FDI attacks are constructed. So that's kind of an interesting takeaway that we see in the results. So, so to sort of summarize that, so we can only localize to the neighboring buses, and that makes sense. And all 3 autoencoders perform about the same. And so because the compromised device affects the reconstruction on neighboring devices, this approach like may not be the optimal method to localize to the exact devices, but it will give you like the bus and the neighboring buses. And so probably going forward, what would be good is to combine this with another method, or do something else as well on the localization side. And yeah, here's a picture of the system that I think kind of helps with sort of picturing what I'm describing. So let's see, the devices with the red circle are the ones that are actually compromised, and then the devices in yellow are the neighboring buses that also get this reconstruction error that gets spread out to them as well. So that's kind of interesting. And so some key takeaways is that these autoencoders are really useful in helping a utility company potentially who does not have a lot of information about the attacks, and it's unsupervised, so they don't have to have label data. And then we also get some benefit of localization as an added advantage to detection, since we don't have to do anything extra to get this localization, but we do get this like spreading out feature to the neighboring buses or devices, which would be expected. And so Arnav left, who was the master student working on this, and I've got some, so the project is still going on, and we're still working on it. I have different students who started this spring, and some of the things we're looking at are larger cases and considering, telling how do you distinguish FDI attacks between other events. And then we're also looking at this localization problem further and some other ideas on the detection.
Thank you, Katherine. Thank you. It's for this very nice presentation on a very interesting subject, the subject of deep learning approach to the false data injection attacks. I see that it is an ongoing project, and I'm happy to hear that, because there's so much to do on that, on the subject. So very interesting. So I will now address the audience for questions. So are there any questions for Professor Katherine? No questions?
I will say I really enjoyed the earlier paper, Theodorus.
Yes, I also enjoyed it a lot. So I was, if there are no questions from the audience, I would ask you one thing that I was curious about. That it seemed to me that you used data from transmission networks, right? And the application framework and use case is a transmission case. But I was wondering if your encoder would work well if trained with distribution kind of data that is much more volatile.
That would be interesting.
Yeah, this is, but of course you didn't try that out, but I think it would be interesting to see if it's under very volatile data, the dynamics are probably harder to capture, and I think it would be interesting to see if it works.
Yeah. Yeah, that's interesting. Yeah.
So we have a question from the audience. So let me read it. The question goes like this: can you share current standard practice on anomaly detection and its importance? So it's the question a bit.
So current practice on anomaly detection. So I guess it sort of depends on exactly what this anomaly detection problem is in the utility. So I think right now utilities are very siloed in that, like, different parts of the organization tend to focus on specific problems and specific data sets. So the anomaly detection question would probably depend on exactly like which thing it is that the utilities are trying to detect an anomaly for. If it's false data injection attacks, as far as I know, well, there is some ongoing work trying to do something similar like this for utilities. I don't know how much is actually being done right now on this. I think it may be changing rapidly though. I think this problem and like visibility into the problem and how to like solve it at scale has like been gaining a lot of traction. So I think it's like going that way. But definitely this is like very different than the traditional state estimation based bad data detection that like looks at a single snapshot and couldn't detect anything if there's coordinated measurement compromise.
Okay, so there are no other questions. Kate, so I just want to thank you for the presentation, and we'll move to the next speaker. Thank you so much. So the next speaker is Xiao Chen, also known as Mark. So he's currently working towards the PhD degree in civil engineering